So in this example, I want to show you another way to look at these, and that is by looking at the critical values and the test statistic. And I want you to see the relationship there. There's a question on the final, and there are several in my math lab that ask about critical values and using the test statistic to determine either confidence levels or if we should reject or fail to reject the null hypothesis. So let's look at one. So national poll from the Pew Research Center, data just 7/23/2012, found that the percent of U.S. adults 18 to 25 who have at least one tattoo is 36%. And a researcher at MTSU doesn't know if the rate of MTSU students is higher or lower than this. And so suppose they ask 300 randomly selected MTSU students if they had a tattoo. And of these 300 polled, 126 stated they had at least one tattoo. Run the appropriate test at the 0.05 level of significance to determine if there's enough evidence to conclude that the proportion of MTSU students with at least one tattoo is different than the 36%. And if it is, let's run a confidence interval to determine plausible values. So let's go ahead and state the null and alternative hypotheses. This is usually where I begin on these. So we are looking for HO, and so HO is going to be that it's equal to sort of the status quo. In this case, 0.36. Okay, so there's HO that P equals 0.36, that the proportion is 0.36. Now what about HA or H1? So we're unsure of the rate if it's higher or lower. If we knew, if we had a suspicion that it was higher, then we would say P is greater than 0.36. If we had a suspicion it was lower, we'd say it's less than. But since we don't know, we're going to use the not equal to. Okay, so now we have that. Now we need to look at our conditions. Now, I'll be honest with you, most of these conditions are gonna be met in the problems that you face, but we still need to, at the very least, mentally go through them. And the only one you really have to check for this class is going to be this first one. And that is, does n times p times 1 minus p, is it bigger than 10? Because if our sample size is too small, we're not going to be able to use the normal approximation to the binomial to get this to come out. And so we're looking at, is n times p, 1 minus p, bigger than 10? So it's 300 times 0.36 times 1 minus 0.36. Is that bigger than 10? You crunch it on the calculator, you find that it is bigger than 10. So we're okay with that one. And then we have a few more conditions that you, at the very least, mentally make a checklist of these. And that is, we assume independence, that we are not I'm sampling from that people aren't really related in some sense, that just because we pick that one person picks, say they have a tattoo, that the other person can have a tattoo. Maybe they're married, and married people end up having more tattoos together. If one of them has it, the other one has it. So we want to eliminate that. We often just have to assume independence. It says they were randomly sampled, so we're okay there. And the sample is less than 5% of all of the population, which in this case is MTSU. So all those conditions are met. Again, the one you're going to have to check in this class, the only mathy one you got to check is this one right here. So go ahead and make sure you check that. Now what are we going to do? So we're looking at proportions. We have one proportion that we're comparing to a population proportion. So this is going to be the 1 prop z test. So with the 1 prop z test, we're going to have to find a test statistic. Often in the class, all we care about is the p-value, but in this technique, I want you to look at the test statistic, and we're going to compare that to the critical value. So let's first look at the critical values. Okay, for the sake of space, I'm going to just kind of move some of these things out of the way. So we've looked at this before, possibly with the confidence intervals. So if we have a confidence interval, if we're looking for a confidence interval of 90%, it corresponds with the critical value of 1.645. And let's just kind of think about this. Let me pull this up here. So let's remember what these critical values mean. If I've got a 90% confidence interval, so that means I've got 90% from here to here, for instance. What do I have left in the tails? So 5% here, 5% there. So I've got 10% left in both tails, and that is my alpha, right? And what's 10% divided by 2? 0.05. That's sort of where that notation comes from. And so what critical values, what z values correspond to a 0.05? Let's go ahead and stick a mean in here. Ends up being 1.645 approximately. And same thing over here, negative 1.645. Okay, very similar with the 95%. So with 95%, I'm going a little bit further out, and it ends up being 1.96. So the value here is 1.96. And these regions here are the critical regions. Now let's say if we're given a non-standard one to find, it's not a problem. So we're going to go second distribution, and let's do the normal CDF command. And let's just sort of prove that this worked. Okay, I think I said normal CDF. I meant to say inverse normal, because we are given the 95%, for instance, or the 90%. Let's just look at the 90%. So if we're given 90%, and I'm asked to find the critical value, or if I'm given alpha is 0.1, I'm asked to find the critical value, or the z alpha over 2 value, I'm just going to go inverse norm. It helps me to have this curve drawn out, just so I can mentally see this. If it's a 90%, that means I've got 5% here, so I'm doing inverse norm of 0.05. And I get negative 1.6449, which is pretty close to negative 1.645. Now, when it asks for this critical value, they always give them in the positive. So we just turn that into positive. About the 95%. So with 95%, second distribution, inverse norm. 95%, let's say if we don't want to do 0.05 divided by 2 in our head or ahead of time, we can just put 0.05 divided by 2. And I get about, well, I get exactly negative 1.96 in this case. Okay. And same thing for 99%. We'll go ahead and do that. So inverse norm. And 0.01 divided by 2. Okay, so 2.576 officially. This book and many others say 2.575. It'll be close enough for what we're going to be doing here. Now let's say they gave you 98%. So then you would do 98% would correspond to an alpha of 0.02. And so you would just do inverse norm of 0.02. Whoop, divided by 2. About 2.33, and so forth. And they'll tell you how much to round, what the rounding needs to be. Okay, so let's go ahead and go back to our problem, which is kind of a reminder of these critical values. So our problem, we're looking at 95%. So it is going to be right in here. So this is our critical value. So if it asks for the critical value, we're going to say 1.96. And again, what does that mean? Let's put 1.96 on here. 1.96. And this is why it's kind of more powerful if we can have a one-sided test. It gives us more area in order to reject HO. That's for another lecture, though. Okay, so we need to find if our value, if our test statistic, our z in this case, falls in this critical region. Then that means that I'm going to be able to reject HO. It is significantly different. If it doesn't fall there, in fact, we don't really know. It could be over here too. If it doesn't fall into that critical region, then we fail to reject HO. Okay? So let's compute that test statistic. Now, I'll do this one by hand. I'm not going to make you do these by hand, but it may help you sort of see how we compute these and what the calculator is doing. So I'll show it to you by hand real quick. I've already done ahead of time. And then I'll show you in the calculator where that test statistic actually shows up. Okay, so there's our formula for the test statistic, right? This is just finding the z. So it's p hat, the sample proportion minus the population proportion. Sometimes I'll use a p sub 0 here. Divided by the standard deviation. Now here's the formula for standard deviation. P times 1 minus P over M, and take the square root of that. So we plop all that in. We get our test statistic at 2.16. Let's see how this compares to when we use the calculator. Okay, so I'll bring the calculator in here. We'll press Stat, go over to Test. This is a 1 prop Z test. I'm going to put in 0.36, 126, 300, and let's crank this down. This is not equal to, and let's just click Calculate. There's our Z. It's always been there when you've been doing these tests. I just don't always explicitly ask for it. Occasionally my math lab does. Maybe I should be asking more of this. So it's about 2.165. So we have a little bit of rounding error here, but that's okay. So about 2.16, 2.17. So the question is does this fall in a critical region? If it does, I'm going to reject HO at the 0.05 level. And look at here, we have 1.96. It's going to fall just to the right of that, right? So somewhere in here. There is 2.16 right here. It is in my critical region. It is greater than my critical value. So we'll often say because 2.16 is greater than the critical value of 1.96, I'm going to reject HO. It's a J. Reject HO. Now look at the connection here. So what's our p-value? Our p-value is 0.03. So we would also reject this based on our p-value that's given of 0.03. Because notice we're at the 0.05 level. And here is a p-value that is less than our 0.05 level of significance. So we reject it based on that. You know, it used to be that we had to do all of our problems pretty much this way because it was hard to get exact p-values prior to calculators and computers. Even with computers, most students didn't have computers with the software on it. Now it's free. It comes free with my math lab anyway. So this is how it works with critical values. It's important that you sort of maybe see both ways. I think in the future I'm going to include many more of these in the beginning and then let you sort of choose which way you want to do it. But there is a question on the final that does make you make this connection with the critical values. So you'll make sure you need to find that and see if it's bigger than or less than your test statistic and see if it's bigger than or less than the critical value. I hope this helps. Okay, I wanted to remind you on how to do the confidence interval. It also asked for that too, so I want to finish up the problem. Let me remind you our p hat, our sample was the 126 over 300. That 6 didn't come out too good. Which was equal to 0.42 or 42%. Okay, so let's use our test statistic. Sorry, not our test statistic, our critical value to create a confidence interval. Okay, so the formula, it may look a little nasty to you, but this is it. So it's p hat, it's our sample proportion, minus, this is for the lower bound of the confidence interval, minus our critical value, z alpha over 2, times the standard error, the standard deviation here, which is the square root of p hat 1 minus p hat over n. Okay, you plug those numbers in, 0.42. Remember, we got our critical value of 1.96 because that's at the 0.05 level of significance. And then just run it through, and you'll get 0.364 for the lower bound. Similar for the upper bound, except for instead of subtracting, we're going to add. Okay, so for our upper bound, it's just p hat plus z alpha over 2 times the square root of all that. Plugging that in, it's going to give me about 0.476. I'm just rounding to 3 decimals here. I usually go one more than what I did up here. Okay, so there's our confidence interval. So we would just write this as 0.364, comma, 0.476. So we are 95% confident that the true population, or sorry, the true proportion of MTSU students, the population of MTSU students that have at least one tattoo is between 0.364 and 0.476. And notice that we can actually use confidence intervals for hypothesis testing. Notice that 0.36 does not contained in our interval. So we are, again, based on the confidence interval, we would reject the null hypothesis that it was equal to that. So there are a couple different ways we can run hypothesis tests. Now let's see how this compares if we do it on the calculator. So I'm just going to go to Stat, Test, and this is the 1 prop z interval right there. I already have it in there. Confidence interval, we are at 95, and let's calculate. So we get exactly the same thing, 0.364 and 0.476, because they use the same formula in the back end. So I wanted you to see how some of these pieces connect. Sometimes when we use the technology, that is lost, and I hope that this has helped. I recommend maybe going back and doing 1 or 2 problems where it doesn't ask you all this, to use the critical value method and check it on the calculator, and I think you'll get exactly the same results with maybe maybe off due to some rounding.